welcome back to the course. Now let us look at how 2D NOE experiment the peak pattern comes about. So, we looked at briefly at the theory of NOE in the last class. We saw that to transfer magnetization from one spin to another, we use the 3 pulse experiment 390 degrees, and between the second and the third we use a delay called as mixing time. This mixing time is very useful important parameter which we will see again when we look at 3D experiments or when we look at the structures of biomolecules. So, for now let us see how does this peak pattern look in a NOESY experiment. So, let us take again this simple molecule here, propyl chloride. Here you can see that these 3 protons are again close to each other, which is this to this will be about 2 to 3 angstroms and this to this will be about 4 angstrom, 4 to 5. It can't be more than that. So, all of these 3 are close to each other within that limit of 5 to 6 angstrom which we saw in the previous class. So, let us say now I record a 1D spectrum, and again let us ignore this J coupling pattern in this particular spectrum. We are not interested in that will be present, but we are not going to look at it, we will not analyze that. So, 3 2 1 is this is the 3 peaks which are seen, again this is based on the inductive effect. 3 is again very far from chlorine. So, 3 will come close to the 1 ppm, 2 is in the middle and 1 is close to chlorine. So, it is de-shielded. Now, suppose I record a 2D NOESY spectrum of this molecule. So, this is how it will look. So, first is that both these axes here are protons, because we are transferring polarization in a NOESY experiment from proton to proton. So, now first thing you will see is the diagonal peak. Now, diagonal peak is this is similar to what we saw in the 2D COSY TOXY experiments, where what is this coming from? This comes from the fact that this spin, let us say 3, does not transfer any magnetization to anybody, part of it. So, part of it is kept with itself and only part of it is transferred to 2 or 1. So, whatever is not transferred to anybody and is retained on itself, that part of the magnetization ends up as a diagonal peak. So, this is, let me go back a slide and show you this experiment with reference to that. So, here we saw that when you apply this 90-degree pulse, during this mixing time the magnetization is actually polarization is transferred from A to B, but that is not 100%, there is only about 1 to 2%, remaining 90-95% actually remains on A. So, the bulk of it, the majority of it still is on A, only a fraction of it is transferred to B, and what is transferred is what we actually detect, and what is not transferred is also detected. So, both of them are detected, but the one which is not transferred is essentially nothing but a diagonal peak. It has no information, it does not have any useful information for us, because it is just telling us 3 is connected to 3, which is what anyway is a known information, there is nothing to new about this. Similarly, 2 at 1 all the protons will have the corresponding diagonal peaks, and this is something you should very well keep in mind. In fact, there is an area of research in NMR, as I also alluded in the previous classes, is to how to get rid of this diagonal peak. There are several papers published known as diagonal-less NOESY spectra, and because this, as I said, is almost 90-95% of the signal is coming to the diagonal peak, only a very fraction of it is in the cross peak. Now, what is a cross peak? Cross peak is the peak where there is a transfer of polarization between 2 spins, and this is something which we saw even in COSY and TOXY. So, let us look at this spin number 1. It is in close proximity to 2, which is expected because there are only 3 bonds away. So, in a NOESY spectrum you will see a cross peak between 1 and 2. Okay, so, this carries actual information of the distance, because only when they are close or less than 5 to 6 angstrom you will get a distance. Not only that, the intensity of this peak, the area of this peak is also related to the distance between these 2 spins by that formula which I showed in the previous class, that is I is proportional to 1 to the power 1 by r raised to 6. So, by looking at the intensity or integral of this peak, I can also estimate the distance with actual distance between the 2 hydrogens. We will see that part later when we come to the structure calculation of proteins biomolecules, where we actually do that. We need distance information from NOESY. So, that is based on the area integral of the peak. But one thing is, if you notice, just having a peak itself is enough to tell us that these two protons are within 5 angstrom. If there was no peak between these two hydrogens, that means they are away from, or they are farther from 5 angstrom. So, you see already the distant information is already coming in without actually calculating the distance. We already know just by the presence of the peak that these two hydrogens are close in space. So, this is actually the strength of this experiment, that by just looking at the spectrum we are able to get the information of which hydrogens are close to which hydrogen. The actual distance will not matter so much, as we will see later. What matters is just the information whether two protons are close or not. So, now let us go further. If you look between 2 and 3, again this 2 and 3 are definitely close to each other. So, you will get a cross peak between 2 and 3, is similar to between 1 and 2. Now, between 1 and 3, as I said, they are also very close, because this is not very far away, it is less than 5 to 6 angstrom. So, therefore, magnetization of 1 is also transferred to 3 by NOE effect, and therefore, between 1 and 3 again you will see a cross peak. So, this looks like a TOCSY pattern. So, TOCSY and NOESY actually look very similar if the within one molecule. So, if you record a NOESY or a TOCSY of one molecule, let us say in your sample, and this is a small molecule where all the protons are within 5 to 6 angstroms, you will not see a big difference between TOCSY and NOESY. But if you go to a larger molecule such as a protein or biomolecules, there what happens, as I showed in the previous class, that the two protons may be very close in space, but they may be very far in the sequence. So, in such cases the TOCSY peak will not come between those two protons, because they are very far in terms of bonds, but they will appear in the NOESY spectrum because of very close in space. So, the proximity matters here, and not how many bonds or how much is the J coupling. This is a very important point to keep in mind. So, this is what I showed. Let us say if you have a long chain, this is something like a protein, and you have a chain which goes very long, and but it comes close in space to one of these protons. For example, is shown here. Let us say I have a hydrogen which is a methyl, and show something is, this is just an arbitrary signal, it is an example. So, do not think of it as literally this structure. This just shows that there is a long chain, and therefore, it curls or comes back because of the geometry of the molecule, and because of now it is close proximity to 1 and 2. So, if there is close to 1, you can see there will be a new peak now appearing between 4 and 1. But 4 and 1 are no longer J coupled, there is no J coupling between them, it is only the through space interaction which is basically dominating, and that gives rise to a peak. So, this information that 4 and 1 are giving a cross peak is already a very good information, because it tells us these two hydrogens are close in space. So, this is the kind of information that NOESY experiment can provide us. So, you can see that this peak would not have come in 2D TOCSY, because 1 and 4 are far away in terms of bonds, and they are not part of the same spin system. So, if you recollect the concept of spin system in TOCSY, we said that those network of protons, a family of protons which are coupled to each other by J coupling, we call them as a spin system. But here this hydrogen and this hydrogen are no way connected by J coupling, because this is very far. So, this they do not belong to a single family, and therefore, they are two different spin systems, they belong to two different spin systems, but still they will give a peak because they are close in proximity or space. So, this is basically the central idea, and the next point is what I said in the just a few minutes ago, that we can use the intensities or area, the integral or volume of the peaks to get the distance information, and we can ignore this diagonal peak. This diagonal peak has no information none for us, and therefore, it is not required to analyze the diagonal peak, but sometimes the diagonal peak and the cross peak, they come very close to each other, and when that happens there can be a severe problem. What happens is the high intensity of the diagonal peak starts dominating, and it starts hiding the cross peaks. When that happens, you can no longer use the cross peaks intensity, because they come very close to the diagonal peak. We will see some of the real spectra later on to get a feel of how strong this and diagonal peaks are. So, in such cases, as I said, there has been a lot of research conducted to remove this diagonal peak by some method, so that we can get a clean cross peak intensity. So, now as let us come to this second experiment, which is alternative to NOESY, and this is also a very important experiment in case of small molecules and peptides. We saw that in the NOESY experiment does not work, the NOE effect, not the experiment as such, but the NOE effect itself fails if your omega into tau c is equal to 1. So, this was the problematic condition for certain molecules, and as I showed you that it happens typically for peptides. Peptides will come in this range, it is 8 or 9 or 10 amino acids for such kind of molecules at this kind of frequency. So, remember, if I change the frequency, this effect is not there. So, it depends on both the frequency and the rotational correlation time, and the rotational correlation time we saw in the last class is depends on the molecular weight divided by 2, molecular weight in kilodaltons divided by 2 is roughly the rotational correlation time in nanoseconds. So, if that happens, the NOE effect becomes 0 if this equation is omega tau c is close to 1. It does not have to be exactly 1, even 1.1 or 0.9, the effect starts reducing. The NOE is perfectly 0 at 1, but above and below 1 also it can be close to 0. So, in such cases what do we do? So, there are two possibilities again which we discussed in the previous class. One is we can change the temperature. So, if you change the temperature, you can actually go to a lower or higher tau c value. So, let us say if I increase the temperature, my tau c will decrease, or if I decrease the temperature, my tau c can increase. So, by just changing the temperature, I can come out of this condition if it happens for a particular molecule. Or I can change the spectrometer frequency, I can go to an 800 megahertz or a 200 megahertz, I can go down also, but normally we go to higher frequencies because of sensitivity reasons, and therefore, higher spectrometer frequency can also help us to come out of this condition. So, now during this experiment, so in this particular ROSY experiment, how do we perform the experiment? This is now different from NOESY, completely different in fact. In a NOESY we use 3 pulse experiment, that is 90 90 90. Here there is only one pulse and a set of pulses which is called as isotope. This is actually the same experiment like TOXI. So, if you recollect the TOXI, the class where we did TOXI experiment, discuss the TOXI part, we saw the pulse sequence was exactly like this. So, a TOXI and a ROSY you might think actually are similar experiments, but there are small differences in terms of the power levels and the mixing time. So, in a TOXI experiment, the mixing time is typically, as I mentioned in that class, is about 80 to 100 milliseconds or 60 to 100 milliseconds, and that depends on the strength of the J coupling between the protons. But in a ROSY experiment, we use much longer mixing time. You can see here 200 to 500 milliseconds for small molecules. But if I use such a long mixing time and I use the same power level as a TOXI, it is a problem. It can create a heating in the sample. So, the radiation is actually not very strong, is much weaker compared to a TOXI. In a TOXI we use stronger RF intensity because of what is called as mixing. We want to have a stronger mixing, but in a ROSY that condition is not necessary, and we actually use a very low power compared to TOXI, and that is called as a spin lock. We also use the word spin lock. This is similar to TOXI again. So, all the terminologies which you see in TOXI and ROSY are same. So, this is called a spin lock period. So, during this spin lock, the magnetization again are transferred between each other, but this is not from J coupling because we are not using the same J interaction. The strength of the isotropic mixing is not strong. So, the TOXI effect is not so high here, although the experiment is same, but we have changed the parameters. So, here now because of a longer and a weaker mixing, there is a through space interaction which happens. So, the spin actually is in xy plane. So, remember we are not in the z axis. So, like in the NOESY. So, first we excite the RF pulse, the spin with an RF pulse. So, this is like any other experiment. The spin is now in the xy plane, when it comes to the xy plane, it starts evolving because of the frequency, and that can be actually written as I can show you here. We can write it as cosine omega a t 1. This is same as nosy, and during this period there is a transfer of magnetization from A to B, and that where B is a spin which is close, again close in space to A. So, again this same idea applies, it has to be less than 5 to 6 angstrom even in a Rosie experiment. So, Rosie and nosy are not different in terms of the distance information that we can obtain, it is similar, but the main difference is here you can see here it is in the xy plane. So, here it is in the xy plane, whereas in the nosy we transfer the magnetization to z axis. So, I can write here nosy is a transfer of magnetization happens along z axis when the magnetization is along z axis, and in a Rosie it happens when it is in the xy plane. So, this is the major difference between the two experiments, one is along z and so therefore, in a nosy what matters is a T1 relaxation, because remember T1 is what is governs the relaxation along z axis, and T2 in case of Rosie, because T2 the relaxation is what dominates in the xy plane. So, when you are in the xy plane and the T2 relaxation matters, whereas when in a z axis T1 matters. So, in a nosy experiment we saw that our T1 should be long, we cannot use relaxation, the mixing time cannot be chosen arbitrarily, it depends on the T1 of the sample and considerations such as spin diffusion. Same thing happens in Rosie. In a Rosie also you are now the mixing time. So, this is a mixing time here which I wrote as 200 and 500 milliseconds, 200 to 500 milliseconds. It depends on the T2 of your sample. If the T2 is short, then Rosie experiment will not be very sensitive. If T2 is long, which happens in the case of small molecules, and definitely we are working with small molecules in case of Rosie, we do not use Rosie for proteins, we use Rosie mainly for peptides and small molecules, and in such cases the T2 of the molecule will be sufficiently long. So, that condition is not a big critical factor. At the same time what we want to do is we want to we do not want the spin diffusion effect, which I discussed and we will discuss that later again, where the transfer happens beyond the two spins which are more than 5 angstrom, but still transfer happens because of the intermediate nucleus, and that can be avoided by choosing a appropriately short mixing time. So, that is something which one has to optimize. This number is something which is not a priori known for any given molecule. So, one typically does what does is he records for a series of mixing time, and based on that we can decide whether which particular mixing time is the most appropriate. So, we will see that when we come to the practical aspects of structure determination in proteins and biomolecules. So, this is a spectrum example for a Rosie. So, you can see here the main point to take home is the cross peaks are opposite in sign with respect to the diagonal peak. We will look at this chemical exchange part a little bit later. So, now this is the important point which we do not see in nosy. So, in a nosy experiment the cross peak and the diagonal peak, they have the same color, they have the same phase. So, if this is black, the nosy cross peak also would be black, but in a Rosie the cross peak is opposite. And why is this so? And this is a little technically involved answer for this, and that is the cross relaxation sign. So, what happens typically when you have omega tau c less than 1, which is in the case of small molecule, your cross relaxation, or in nosy typically what happens is the cross relaxation is can be positive or negative, but in a Rosie the cross relaxation is always positive. So, because of that there is a change in the sign which we cannot go into detail, unfortunately it involves mathematically solving some matrices, and that is not the object of the course. The objective of the course is basically to get an idea how the Nosy experiment and Rosie experiment works, what are the type of peak patterns we get and how do we analyze it. So, in the case of Rosie, the diagonal peak and cross peak are opposite. What is one more thing is the spin diffusion peak. So, this is something which I mentioned, that suppose I have A and going B and C. Let us say I have 3 spins and this is between, let us say 5 Armstrong or 4, and let us say this is about 4. So, this to this probably is about 6 to 8 depending on the geometry. So, obviously between A to B A to C I cannot expect any cross relaxation or any NOE effect or ROE effect, because ROE or it is Rosie and Nosy both have this constraint of this distance. But still I may end up seeing a peak between A to C, and this is something which I refer to as the spin diffusion effect, which basically says that the magnetization has gone from A to B and then it has gone from B to C during the mixing period. So, it looks as if the magnetization actually has come from A to C. So, this is what typically a mistake happens in interpretation in Nosy, is that I may see a cross peak between A and C, but actually A and C are not really close. And why do I get that peak? That by peak comes because A to B is, there is an intermediate, a middle nucleus B here, which can relay the magnetization from A to C through B, and that happens because if I choose a long mixing time, that effect can happen, and therefore, you may end up interpreting or analyzing the C and A cross peak as saying that they are closer than 6 to 8, closer than 5 Armstrong, and which can be a wrong structure now, because actually in reality they are not less than 5 Armstrong, they are actually far away. So, this is called a spin diffusion effect, and Nosy is very difficult to find out. Well, one can do some experiment, for example, one can reduce the mixing time slowly, gradually and systematically, and see if that cross peak of C disappears, because the cross peak of C, it depends on how long you choose the mixing time. So, that is why we, as I said, one has to optimize the mixing time. In a protein, typically in general we use about 60 to 80 milliseconds in a Nosy, whereas in a peptide in Rosie is we typically use about 200 to 300 milliseconds. 500 is for a smaller peptide, very small tripeptide, or for a small molecule we can go up to 500, but this has to be optimized for spin diffusion problem. But in Rosie, one strength of Rosie is that the cross peak is opposite, number 1, which already we saw. Not only that, the spin diffusion peak, that is from A to C, will be positive again, that means it will be same as diagonal. So, diagonal and spin diffusion peak is not shown in this graph, I do not see any spin diffusion peak, but if there was a spin diffusion peak, it would have come, the cross peak would have come and the same color sign as a diagonal peak. So, the spin diffusion peak also becomes opposite to the cross peak. So, this color changes based on whether it is a direct peak meaning A to B is a direct peak because they are close than 5 Armstrong, B to C is also a direct peak because they are less than 5 Armstrong, but A to C is an indirect peak. There is no direct dipolar interaction between A to C. So, that is a spin diffusion peak, and interestingly in Rosie the cross peak between A and C, cross peak, I am not talking about diagonal peak, cross peak between A and C will be the same color as the diagonal peak of A and C or any diagonal peak. So, that way by changing the sign, that phase, that we use technically the correct way to say is the phase of the peak now tells us whether it is a cross peak or a diffusion peak, and that information is not there in Nosy. So, unfortunately Nosy, although is very useful for proteins, does not carry that information of spin diffusion, which very routinely happens when we make a mistake in choosing the right mixing time, but in case of a Rosie it very beautifully brings it out. And there is another effect called chemical exchange which was mentioned here, and this is something which right now I will explain in a brief manner, but we will take it up later toward the end of the course when we study protein ligand interaction. So, exchange is a very simple idea. Exchange is a molecule A is undergoing an exchange or a conformational or a structural change to another state. So, same molecule A is undergoing a conversion to another molecule. It is like, for example, the ketoenol in organic chemistry. keto-enol transformation is a kind of a structural change or conformational exchange between two different structures, but the same molecule is undergoing. So, this can happen slowly, the exchange can be slow or exchange can be fast. So, this fast and slow depends on how the chemical shift difference between A and B and the rate of this reaction. So, remember when we say fast or slow exchange, all depends on how close the peaks of this spectrum. If A and B are very close, then it is very difficult to figure out the exchange, the exchange will always look very fast. But if the A and B are far away, if their A is well separated from B, then we can decide whether the exchange is slow or exchange is fast or exchange is somewhere in between, that is called intermediate. So, there are different levels of exchange, we use the words like fast exchange, slow exchange, intermediate exchange, and all of this is very important in biomolecules because biomolecules are constantly always in exchange with different states of the same molecule. Okay. So, there is nothing like a single structure of a biomolecule. Biomolecule always has multiple structures and each of these structures are now exchanging with themselves through different exchange rates, and therefore, it is a dynamic system, and that depends now very well. Now, that will be reflected in all your experimental, for example, in NOESY especially, if the molecule has two distinct states and the exchange is slow, suppose the chemical shift difference is very high and the exchange is slow, then you will start seeing a cross peak between those two states A and B. Okay. So, that gives us the information about that there is an exchange going on between the two structures of the same molecule. The exchange is in the slow or fast, that depends on, as I said, the chemical shift difference and the exchange rate. Now, this also depends on the temperature. If I lower the temperature, I cool down the sample, the exchange rate will slow down. If I increase the temperature, the exchange rate will go up. So, by changing temperature, one can actually analyze the exchange rates and that is how it is used. But ROSY is not the only experiment. ROSY chemical simple NOESY experiment can also be used, but here the point is that the cross peaks as exchange peak will look same as a diffusion peak. So, exchange and diffusion again can be confusing. If I see two black peaks here, suppose I see a black peak here where the arrow is pointing, the black peak can denote either an exchange peak between some other species or it can denote a spin diffusion between two peaks. So, we will not go into many more details of this experiment. ROSY basically will stop here because this is essentially for small molecules and peptides. Our focus in this course is going to be on larger systems such as proteins, where we have about 50 to 100 amino acids, and such larger protein systems we do not need to do ROSY, we will be only doing NOESY experiments. But the idea here was to show you that there is an alternative to NOESY, that is the ROSY effect, and it is very similar to TOXY. So, there has lot of been papers published where they have actually shown how the TOXY effect can be removed from the ROSY spectrum. So, as I said, in ROSY you can also end up getting TOXY peaks because TOXY also is the same experiment, although the parameters or the pulse levels, I mean the power levels are different, but still there can be a leakage problem. TOXY peaks can show up, similarly ROSY peaks show up in TOXY, but that there has been lot of developments and lot of research papers which have gone into this on addressing this point. So, in the next class we will look at the heteronuclear NMR now. We have completed the homonuclear NMR experiments. We looked at 2D COSY, we looked at 2D TOXY, 2D NOESY, 2D ROSY. These are the main 4 experiments which are very typically used in homonuclear experiment molecules. But when it comes to biomolecules where we have carbon 13 and nitrogen 15, definitely we need to use heteronuclear NMR experiments, that is has much powerful or more information. From there we can actually build 3D NMR which also we will see in this course. So, we will start looking at 2D heteronuclear NMR experiments from the next class.